we present perception stitching, a method for zero-shot perception encoder transfer for visuomotor robot policies. A policy trained with one camera setting usually cannot adapt to another camera setting. How can we reuse the learned knowledge of the same task and enable efficient transfer to different visual observations? We want to enable zero-shot transfer of the trained policies to a novel combination of perceptual configurations. However, the different latent representations make the directly reassembled policy malfunction. In the perception stitching process, we train two policies with different camera settings, and then stitch them together to get a reassembled policy for a novel camera setting. We observe that there is an approximately isometric transformation relationship between the corresponding latent representations. To align the latent space, we select a set of anchor images and embed them through the visual encoders. Then, we calculate the cosine similarity to get the relative representation. The relative representation can ensure an approximate invariance at the latent space. We also apply a disentanglement regularization to further refine the latent space alignment. We evaluate our method on 4 real-world manipulation tasks. On the staking task, we achieve 45% of success rate. On the lifting task, we achieve 80% of success rate. On the pushing task, we achieve 85% of success rate. On the reaching task, we achieve 100% of success rate. We also evaluate our method on 30 simulation experiments. We achieve 92% of success rate on the pick and place task, 90% of success rate on the cube staking task, 100% of success rate on the pushing task, and 91% of success rate on the lifting task, and 48% of success rate on the door opening task. Our method consistently performs better than the baselines, especially on the more difficult tasks. We also conduct latent space analysis to review the mechanism of our method. We find that the latent representations with our method have similar shapes with each other, while that of the baseline do not. We also compare the distances of the latent representations. The cosine and L2 distances with our method are generally smaller than that with the baseline method. In addition, we visualize the attention heat map of the visuomotor policies with GradCam. With our method, the reassembled policy can focus on the target object and the robot and effector, while the baseline policy cannot focus on meaningful regions. In conclusion, perception stitching is a method for zero-shot visuomotor policies transfer by latent spaces and alignment. It aligns the latent spaces of different visual encoders and allows the trained visual encoders to be reused in a plug-in and go manner. Evaluation on various experiments shows the pronounced advantage of our method, and our analysis further reveals the mechanism of its superior performance. Thank you.